Hello, you're welcome. All right, introduction to material science. Okay, so we'll start with the definition as usual. Okay, now, anytime you want to define any particular phenomenon um, in engineering or sciences, okay, you should just first of all understand the word that make up that subject. Okay, so now it is called material science. Of course, you know what science is. Okay, science is the study of structure and behavior of a physical system or any of matter. Okay, study of structure and behavior. So now here we are dealing with material science. So the study of the properties, okay, or structure of a material is basically uh, what material science is all about. So it's a branch of sciences that studies material. So now let's actually look at the definition we have here. Okay, so material science involves investigating the relationship that exists between the structure and the properties of a materials. Okay, the relationship that exists between the structure and the properties of a material. Okay, for example, okay, we in material science we look at why materials have their properties. What is behind? Okay, what is the science explanation of the property that that particular material have? Now, beside material science, we have what is known as material engineering, right? Which is like a bit different, okay, or quite different from material science. Okay, now in material engineering, okay, it actually involve um, on the basis of this structure and properties that we've already established in material science. Okay, now a material engineer actually use the basis of the structure and property correlation, okay, to design or to engineer a structure of material in order to produce a predetermined set of properties. Okay, so from a functional perspective, the role of a material scientist is to develop or synthesize new material. So a material scientist actually synthesize new material. Now, whereas the material engineer is called upon to create new product or system using the existing material, right? That is being developed by a material science. So material science actually study discover a particular material based on the relationship between the properties and of course the structure. He studies the property and structure, okay, discover a material, and that material first is of no use until okay it is actually being taken by a material engineer. A material engineer knows exactly the application of such material based on their properties. Okay, their properties of a material will actually determine the application in the field of engineering. So a material engineer will takes that particular material that has been discovered, then I use it to actually design or develop a new system. All right. For example, okay, um, the parts of uh aircraft, okay, the part of aircraft, or let me just use the body of an aircraft, which is actually made up of metal, right? And you know very well the fact that an aircraft will actually have to fly and overcome gravity. The okay, that's one properties that the the body of an aircraft should actually have. The metal. The metal should actually be tough, all right? It should be tough, and of course it should withstand. It should have a very good tensile stress to withstand stress, but at the same time, all right, it should be tough. Okay, so now that being said, a material scientist, okay, a material engineer needs that he need to actually develop the body part of an aircraft that have these properties. Okay, but he doesn't know the material which he needs to actually get. He need to get, all right, to actually build the part, that body part of the aircraft. So a material scientist, being the one that actually investigates different material and their properties, okay, will actually develop a material and having a particular property. Now, a material engineer that knows the property of that material, okay, knowing quite well that it will fit into the design of an aircraft, then he will actually choose that material to develop the body part of the aircraft. So I hope that is well understood. All right. So now let's talk about the structure. Okay. Now, since we said that a material science, okay, actually establish relationship between structure and properties of a material. So what do we mean by structure? Now, the structure of a material usually relates to the arrangement of its internal component. Now, structural element may be classified on the basis of the size. Okay. So now, when we are dealing with structure, is we simply means the arrangement of the internal component, how they are arranged. Okay. And the structure of a material, okay, how the internal component of the material, which is basically the atoms, the molecules or whatsoever, okay, would definitely determines the properties of those materials. So we are going to be looking at those and those the different structural elements, okay, one after the other. Now, the very first is we're going to look at the subatomic structure. So now, subatomic structure, believe that you know what this is in chemistry. Okay, an atom have some atomic particles. Okay, so this actually involves electrons within the individual atoms and their energies. So in the level of a structural element, we can consider the subatomic structure. All right, then no, not okay, their energies, and of course the interaction of the energies of the electrons with the nuclei. Okay, so atomic structure relates to the organization of atoms to yield molecules. So atoms actually combine to yield molecules. So the study of the organization of atoms to yield molecules, okay, we that is actually the basis of atomic structure. Then we now have the nanostructure. Now, in nanostructure, we deal with the aggregate of atoms to form particles. Now, as we go down, right, the size actually increases. Okay. For the nanostructure, right, we are looking at aggregates. So the aggregate of atoms should be such that it should have a nanoscale that is less than 100 nanometer. Okay, it should less than nano. So this simply means that if I have the group of atoms, okay, group of atoms, the aggregate of atoms, depending on how many atoms I'm actually looking at, I can have a nanostructure. Okay. Now, apart from having a nanostructure, I can also have a microstructure, depending on the number of atoms that I have that make up this. For a nanostructure, okay, we are looking at the aggregate of atoms, all right, that should actually be less than 100 nanometer, nm is nanometer. But if we are dealing on microstructure, okay, those are structural elements, okay, those are structural element that are subject to direct observation using some type of microscope. So it is called microstructure because we can actually view it, okay, through the help of microscope. Okay, now structural features having dimension between 100 newton meter, okay, and several millimeter. So that simply means that for a microstructure is bigger than a nanostructure. Okay, of course, you know very well nano is in nanometer. All right, micro should be is ranges from nanometer to several millimeters. Okay, so now a microstructure can actually be viewed and studied using uh, a microscope. So please take note of that. Then you have macrostructure. Now, microstructures are structural elements that may be viewed with the naked eye. So now we have macro, it is bigger than the micro. So you can actually see it by the, okay, through, it can be viewed with the naked eye. Okay. Now they have the scale that ranges between several millimeters, okay, and on the order of meter. So, and of course, any object that is at the scale of millimeter in size, you can be actually be seen with the naked eyes. Okay, so now that is for the structure. Now let's now talk about property. Remember, it is the structural element of a material that determines the property. Now, how do we actually define the property? All right. Now, a property is a material trait, okay, and of what a material trait is like characteristics. So a property is a material trait in terms of the kind and the magnitude of response to a specific input stimulus. So which simply means that a material will actually exhibit some kind of trait or some kind of characteristics, okay, or behavior when a particular stimulus is like a change, okay, in the environment of the material, right? Or some kind of uh, some kind of well, okay, how will I put it? Uh, some kind of changes that is actually applied to that material, which will actually trigger some behavior. Okay, so those behavior, those threat is what is actually known as stimulus. So we simply means that a stimulus is the stimulus, the threat of a material or the property of a material is always triggered. Okay, once it is being triggered, that's when you see it. Okay, generally the definition of properties are made independent of material shape and size. Okay, virtually all important properties of solid material may be grouped into 6 different categories. So we're going to look at different properties and of course the stimulus that trigger those properties. Okay, so now mechanical, electrical, thermal, magnetic, optical, and deuterative. These are one, two, three, four, five, six, okay, 6 different categories. All right, for each there is a characteristic type of stimulus capable of provoking different responses. So all these responses of mechanical, electrical, there's a stimulus that provoke them. So you should not only know the property, but you should know the stimulus that actually provoke these properties. Okay, so now let's look at them one after the other, the properties and the stimulus that stimulate them. Okay, now, mechanical properties. Okay. Now, mechanical property relate to the deformation relate, okay, to the deformation to an applied load or force. Example include elastic modulus, stiffness, strength, and resistance. So, mechanical property of material is investigated when you apply a load or stress on that material. Okay, so the response, that resistance, the resistance that material actually gives to that stimulus, which of course is a force or load on it. Okay, is what is regarded as mechanical property. Okay, and the response is going to be measured based on the elastic modulus or the stiffness of the material, the strength of the material, and the resistance to fracture. Okay, how much resistance it actually offers to fracture. So that is for mechanical properties. Now we have electrical properties. Now electrical properties, okay, the stimulus that is applied is electric field in electrical property. All right, so typical properties include electrical conductivity and dielectric constant. So of course, you know very well that based on electrical conductivity, we have conductors, electrical conductors, and the insulators. Okay. So for electrical conductors, the only way you investigate, okay, that they actually possess the property of conductivity is when you apply electric field. So the stimulus is electric field. Okay. Once you apply electric field, then definitely you will be able to measure their conductivity, and of course you can also measure the electric constant. Okay, now the next we have thermal properties. Now thermal properties are related to the changes in temperature, okay, or temperature gradient across materials. Example of thermal behavior include thermal expansion and heat. So for thermal property, the stimulus is actually heat. Okay, when you supply heat to a material, then it actually responds. Now the responses you have is going to be the threat or the behavior you get is basically thermal expansion, right? And of course, a change in temperature. All right, so that way you'll be able to study the thermal properties of that material. Magnetic properties, of course, you know what magnetism is. Okay, now the response of the material to the application of magnetic field, so that simply means the stimulus supplied, okay, is magnetic field. So the response, okay, now the properties based on magnetic field supplied to a material is basically its magnetic susceptibility and the magnetization. So in magnetic property, we actually measure magnetization of that material, how it can be magnetized, okay, in a magnetic field, or the amount of magnetic susceptibility of that material, okay, in a magnetic field. Then we now have the optical properties. Okay, now the stimulus is electromagnetic light or radiation. Okay, so in optical properties of a material, we're looking at its response, okay, to electromagnetic field or light radiation that is actually incidented on it. So now in that, what we measure is the index of refraction. Okay, of course, same as refractive index. Okay, the index of refraction, of course, we can also measure uh, the reflectivity. Okay, and of course, um, these two properties, these two, okay, you actually use it to measure the optical properties of a material. Then we have the theoretic characteristics. Okay, now the theoretic characteristics relate to the chemical reactivity of a material, for example, corrosion resistance of metals. Okay, that you know very well that most metals are actually prone to corrosion, and of course a corrosion is a chemical activity, it's a chemical reaction. Okay, it's a chemical reaction that actually uh, that take place in the presence of oxygen and moisture. So most metal, when you expose them to the atmosphere, okay, they tends to actually rust, and that is, as they rust, they deteriorate. Rust actually causes the deterioration. So now the resistance of this metal, okay, to this particular chemical activity, actually um, confers to them some deteriorative characteristics or properties. So please take note of that. All right. So now, in addition to structure and properties that we've already mentioned, okay, now two other important components are involved in science and engineering of materials, okay, namely processing and performance. So apart from the relationship between the structure and properties, we can also look at processing and performance. Now, in terms of processing, okay, we are now dealing with how that particular material is being processed, the performance of the material based on its processing, not just the internal structure of the elements, okay, or the component of that material. Right. So now, with regard to the relationship of these four components, the structure of materials depends on how it is processed. Okay, so that means the structure that we get out of material also by depend on how that material is being processed. Okay, so processing method of a material has a very substantial influence on its structure. Now, furthermore, a material performance is a function of its properties. Okay, while the structure of a material depend on the processing of the material. Okay, then then the processing of the material will in turn, okay, the performance of the material will depend on the processing. Okay, now let me go over it again. Right, the structure of a material depends on its processing, right, while the performance of the material depend on its structure. Okay, so a material performance is also a function of its properties. Now, okay, because you know very well that structure, okay, it actually influences the properties of the material. So we present an example of this processing structure properties performance principle in Fig 1.1. Now, photograph showing thin disc, thin disc, thin disc specimen placed over some printed matter. Okay, it is obvious that optical properties, for example, light transmitters of each of these three materials are different. Okay, the one on the left is transparent, though it's still the same material. Okay, so which simply means virtually all the reflected light from the printed page passes through it. So a transparent material will always allow light to pass through it. Whereas the disc in the center on the right are respectively translucent and opaque. So um, processing is actually very important. Now this is the diagram. This is the same material, okay, made, okay, with different processing technique. All right, one is transparent, one is translucent. Okay, translucent simple means that light can pass through it, but you hardly see through it, while the other one is opaque, the same material. So we simply mean that processing of a material will actually um, um, we has a long way. Okay, it actually influences the structure of the material, and because it reflects the structure of the material, it will definitely influence its property life. Now the optical property of this material, this three material, okay, is being influenced. One is transparent, the other is translucent, and okay, this one here is opaque. So please take note of that. Okay. Now the question is, why study material science and engineering? Why do we study material science and engineering? Now, why do engineers and scientists study material science? Simply because things engineer design are made up of materials. So that's just a very simple thing. Okay, every engineering system is made up of material. Okay, be it mechanical engineering system, electrical engineering system. Okay, now many an applied scientist or engineer, okay, e.g. mechanical, civil, chemical, and electrical, is at one time or another exposed to a design problem involving materials. For example, a transmission gear, okay, the superstructure for building an oil refinery component or an integrated circuit chip. This is for electrical engineer, okay? So all these are actually made up of material. So of course, material scientists and engineers are specialists who are totally involved in the investigation and design of materials. Many times, an engineer has the option of selecting the best material from the thousands available, okay? So which simply means that for you to actually any engineering designs, you need the best material, the one that has the properties that fit into that particular system. So okay, you have to choose the best among all the options that you have, the best that can fit into the system. Okay, so the final decision is normally based on several criteria. First, in-service condition must be characterized. Okay, so in-service condition is actually the properties of the material as it is rendering the service. Okay, for this for this uh, detect the properties required of the material. So basically, all aspect of engineering, we need material, and this material, depending on the system that you want to build, okay, there's a material that should actually fit into a particular system. So you have to make a choice to get the best material that will fit into that particular system. So every aspect of sciences and engineering, okay, are faced with the problem of choosing the best material and the best property for a particular system that need to be designed. So I hope that is well understood. All right. Classification of material. Classification of material. Now, solid material have been conveniently grouped into three basic categories: metals, ceramics, and polymers. So these are the major, though there are other classifications, but we have the major classification of material is metals, ceramics, and polymers. Okay. Now, a scheme based primarily on chemical makeup and atomic structure. Okay, so all this scheme of classification is based on uh, the chemical makeup and atomic structure of this material. So that's why we have it classified to metal, ceramic, and polymers. Unlike, okay, which of course is similar to what the classification of element in chemistry, where you have the metals, non-metals, and of course the metalloids. Okay, but here we have a classification where we group material into metal, ceramics, and polymers. Okay, now most material fall into one distinct grouping or another, right? In addition, there are composites that are engineered, okay, okay, and of course, this composite, as the name implies, is actually material that has a combination of two or more different materials. So these are different categories of materials, but in engineering science or in material science, we can take a touch of all this material having different properties of metal, ceramics, and polymers to actually create a composite material, okay, that is made up of these three different categories, okay. So apart from having metal, ceramics, and polymers, we can have composite that is made up of a touch of all the properties of these three categories. So I hope, okay. So now let's start with metals. Right. Now, metals are composed of one or more metallic elements. Okay, so it is metals. They are just made up of majorly metals. Example: iron, aluminum, copper, titanium, gold. All these are metals. Okay, so and often also non-metals. So they might have some small amount of non-metallic element in them. Okay, e.g., some metal might have some small amount of carbon, basically based on their processing. So they might include some carbon, nitrogen, and of course oxygen, but they are in relatively small amounts. Okay, so the major elements, okay, of metals are simply metallic elements. Now, atoms in the metals and their alloys are arranged in a very orderly manner with regard to the mechanical characteristics. Okay, so that is one good structural representation of a metal. They have an orderly arrangement of atoms. Okay, orderly arrangements of atoms. Now, these materials are relatively stiff, strong, yet they are ductile. Okay, so they are stiff and they are strong, and at the same time they are ductile. Now, now, for for instance, they are capable of large amount of deformation without fracture. So you can deform them, you can bend them without fracturing the the metal. Okay, so that is what ductility is: the ability for a metal to actually be bended without being fractured. Okay, so they are capable of large amount of deformation without fracture, and their resistance to fracture, which account for their widespread use in structural. Please pardon me. Okay, okay, in structural applications. Now, metallic materials have large number of non-localized electrons. Okay, now one thing that actually makes a metal different from non-metals is the fact that they have non-localized electron. That is, in chemistry, we call them mobile free electron. Okay, that is, these electrons are not bound to a particular atom. So they have the ability, the electrons are actually free and mobile, and they are not bound to a particular atom. And that accounts for the electrical conductivity of metals. Okay, remember, conductivity of electricity deals with the movement of electrons. So since electrons of metals are not localized, so they have the ability to actually flow, to move. So that is why metals are good conductors of electricity. Now, many properties of metals are directly attributable to these electrons. Okay, for example, metals are extremely good conductors of electricity and heat due to their mobile or non-localized electron, right? And are non-transparent to visible light. A polished metal surface has lustrous appearance. Okay. In addition, some of the metals, iron, cobalt, and the nickel, have desirable magnetic properties as a result of their non-localized electron. All right, so please take note of that. Then we'll now talk about ceramics. Okay, now what are ceramics? Now, ceramics are compound between metallic and non-metallic elements. Okay, so of course, so in chemistry we call them metalloids. Okay, they are structures that you find between metallic and non-metallic elements. Okay, now they are most frequently oxides, nitrides, and carbides. Okay, so most oxides and nitrides and carbides are ceramics. For example, common ceramic material include aluminum oxide, okay, or you call alumina by formula Al2O3, okay, silicon dioxide or silica, silicon carbide, silicon nitride, okay, and in addition, what some refer to as traditional ceramics, okay. So most material known as traditional ceramics, okay, uh, those composed of clay minerals, e.g., porcelain, as well as cement and glass. Okay, so both cement and glass, which of course people refer to as traditional ceramics, okay, belongs to the category of ceramics. So all this, they are all ceramics. Okay, so they are found between the metals and non-metals. Now, with regard to mechanical behavior, ceramic material are relatively stiff and strong. Stiffness and strength are comparable to those of metals. So they, are, they have that stiffness, okay? Their strength can be compared to that of metal. Now, in addition, they are typically very hard, okay? Historically, ceramics have exhibited extreme brittleness, okay? Lack of ductility. Brittleness is lack of ductility, which simply means that um, if they are actually a load, okay, if a load, if a large load is actually placed on them, okay, to some limit, they have a limit to which they will actually withstand some load without fracture. Okay, so if you go beyond that limit, they are definitely susceptible to fracture. Okay, so unlike metal that can actually bend without fracture, but ceramics, if you bend them, you will definitely subject them to fracture. However, okay, new ceramics are being engineered that have improved resistance to fracture. These materials are used for cookwares, cutlery, and even automobile engine parts. All right, so take note of that. Then now let's talk about polymers. Okay, polymers include familiar plastic and rubber materials. Plastics and rubber materials are polymers. Okay, many of them are organic compounds that are chemically based on carbon, hydrogen, and other non-metallic elements. For example, oxygen, nitrogen, and silicon. So basically, they are organic compound, right? Of course, in organic compound, hydrocarbon is made up of carbon and hydrogen, and of course, have so for polymers, they have carbon and hydrogen main element, and also have other non-metallic element, okay, attached to them, which is oxygen, nitrogen, and silicon. Now, furthermore, they have very large molecular structure, often chain-like in nature. Okay, so called that's what they're called polymers. So in chemistry, you know, a kind of what is called polymerization. when you bring is when you bring small chain, okay, small chain molecules of organic compound, then you now use it to produce a very long large chain. Okay, so now that is how polymers are being produced. Okay, so they have a very long chain, okay, long chain of organic compound of hydrocarbon. All right, of course, having some other elements like oxygen, nitrogen, and silicon. Okay, now now the backbone of the chains in polymers is carbon atoms. Now, some common and familiar polymers are polyethylene, please, nylon, okay, polyvinyl chloride, PVC, polycarbonate, PC, polystyrene, PS, and silicon rubber. Now, whereas the mechanical characteristics are generally dissimilar to those of metallic and ceramic materials, they are not stiff or strong as this. Okay, so the polymers are not stiff and strong as the other mentioned uh, categories of materials, which of course include the metals and of the metals and the ceramics. Okay, so we are going to look at more on material science in the next video. Okay, so see you in the next video. Thank you very much.